In this video, we will look at the most basic application of Pythagoras Theorem, performing calculations in right triangles. I assume that you are already familiar with Pythagoras Theorem, but I'll still quickly go over it again, so you can skip that part if you want to. And after that, I'll talk about how we can use Pythagoras Theorem to calculate unknown sides of right triangles. So Pythagoras Theorem applies to right triangles. So that means triangles with one right angle. Such a triangle will always have two sides directly next to the right angle, and we call those the adjacent edges of the right triangle. And then there's one side opposite the right angle, and that's called the hypotenuse. Now, Pythagoras Theorem is about the areas of the squares to those edges. To be specific, it says that in a right triangle, the sum of the squares of the adjacent edges is equal to the square of the hypotenuse. Or if we call the adjacent edges A and B and the hypotenuse C, then Pythagoras Theorem says that A squared plus B squared equals C squared. So for example, when this adjacent edge is 4 and this is 3, then the areas of the squares will be 4 squared and 3 squared, so 16 and 9. And that means that we can also calculate the area of the green square. That will be 16 plus 9 is 25. And of course, that also means that we now know the length of the last edge of the hypotenuse, because the length of the hypotenuse of AB will now just be the square root of 25, because 5 squared would give us 25 again. So using Pythagoras Theorem gives us a way, when we know two of the edges of the triangle, of the right triangle, to calculate the last one. And we're going to look at a procedure for doing this now. So here we have an example. We have a triangle with where we know the adjacent sides. It's a right triangle. We know the adjacent edges, and we want to calculate the length of the hypotenuse. We are always going to follow the same procedure. And the reason is that sometimes we know the adjacent edges of the triangle, but sometimes we will know one adjacent edge and the hypotenuse. And in order not to get confused, it's a good idea always to first write down Pythagoras Theorem for this particular right triangle. So what is this adjacent edge called? And what is this adjacent edge called? Well, this is AB and this is AC. So the hypotenuse is BC. So Pythagoras Theorem for this particular triangle says that AB squared plus AC squared equals BC squared. Now the next step is to start plugging in the values that we already know. What we know in this case is we know the value of AB, of this adjacent edge. AB is 8, so we can replace AB with 8 in the next step. So that means that AB squared becomes 8 squared, obviously. We also know the value of AC, the length of AC, that is 6, so we can change AC into 6. So AC squared becomes 6 squared. And otherwise, there's nothing here to change. So now Pythagoras Theorem says 8 squared plus 6 squared in this triangle is BC squared. We can simplify a bit here because these are numbers that we can calculate. 8 squared is 64, 6 squared is 36. So now it says 64 plus 36 is BC squared, and I can add these two numbers and get 100. So now the claim is simply that BC squared equals 100. Well, if BC squared equals 100, then what can BC be? Actually, strictly speaking, there are two options. BC could be 10, and BC could be minus 10, could be negative 10. But of course, we're talking about lengths, and lengths can only be positive. So the only solution that we actually want to see here is the positive solution. If BC squared is 100, then BC itself must be 10, because 10 squared is 100. So we took the square root of 100 to get to the answer. Now here's a similar example. Maybe it's a good idea to pause the video and try this for yourself before you look at the solution. So let's see how we do this one. So again, the first step is to write down Pythagoras Theorem in this particular triangle. The right angle is D, so the adjacent edges are DF and DE. So the hypotenuse is EF. So Pythagoras theorem says DF squared plus DE squared is EF squared. Now we plug in the values that we want to that we already know. We know the value of DF and we know the value of DE. So now we get 6 squared plus 2.5 squared is EF squared. 6 squared, we can calculate that. 2.5 squared, we can calculate that. 36 plus 6.25 is EF squared. Now let's add these and we get 42.25 is EF squared. And now we can take the square root, and then on the right hand side we have EF, and on the left hand side we take the positive solution, which is 6.5. So now we have calculated that EF is 6.5. What do we do if we see a triangle like this? Well, in this case, we haven't been assured in the image or in the description that one of the angles of this triangle is a right angle. It may look as if angle L is a right angle. Maybe it is, maybe it isn't. We can't be sure. If we can't conclude from the image that angle L is a right angle, then we don't know that this triangle is a right triangle. And that means that we can't use Pythagoras theorem. And in that case, we simply can't do anything about this. So in this case, we don't actually start calculating Km because we don't have enough information. So always watch out for situations where you're actually not dealing with a right triangle. In this case, we are dealing with a right triangle, but we already know the length of the hypotenuse and we know one adjacent side, and we're asked to calculate the other adjacent edge, the other adjacent side. And if we are just as careful as previously in writing this down, then nothing will go wrong. So let's first write down Pythagoras theorem for this particular triangle. The right angle is R, so the adjacent edges are PR and QR, or RQ, as I said here apparently. PR squared plus QR squared equals PQ squared. Which do we already know? Well, the ones that we already know are QR is 3.5 and PQ, which is 12.5. So my equation looks a bit different from the previous ones because now it is one of the two terms on the left that I can't calculate yet. That's not going to be a problem. Let's just go on. 3.5 squared, I can calculate that number, and I can calculate 12.5 squared, and then this turns out to be 12.25, and this 156.25. PR squared plus something equals some other number. Now, in order to solve this equation, we want to have PR squared just on its own on this side and just a number on the other side. So let's subtract the 12.25 here, and we can do that as long as we do it on both sides. So on both sides of this equation, we're going to remove 12.25. And then we are left with, on the left-hand side, just PR squared, as was our intention. And on the right-hand side, 156.25 minus 12.25 is 144. So our equation now is PR squared equals 144. Well, if PR squared is 144, then PR will be the square root of 144, which is 12. So we can also do that. Now it's possible, of course, that we are not so helpful that we actually give you an image or a picture, and we give you just a description like this. In a triangle ABC, we are told that angle B equals 90 degrees, and we know the lengths of two of the sides of the triangle. AB is 45 and AC equals 205. Can we now calculate the length of side BC? Well, in order to write down Pythagoras theorem in this triangle, it's useful to have some idea of where the adjacent edges are and where the hypotenuse is. So whenever you get a description like this, always just make a very quick sketch where you show what the right angle is. So we are given the information that the right angle here is B, and which sides you already know. We know that AB is 45 and AC is 205. And now Pythagoras theorem in this triangle will be relatively clear. We know that AB squared plus BC squared is AC squared, and we will plug in the correct values for AB and AC, and then we get 45 squared plus BC squared is 205 squared. We can calculate these squares, and again, we want to have BC squared on its own on the left-hand side, so let's subtract 2025 from both sides, and we get BC squared is 40,000. If BC squared is 40,000, then BC itself will be 200. So again, if we follow the procedure that we've learned in this video, if we do that carefully, it should be no problem to calculate the missing lengths in right triangles.